So let's say we have n independent particles. So n is equal to the number of particles. And let's say that we have what? M equals the number of constraints. So for example, let's say I have a whole bunch of particles, n number of particles attached to some sort of rigid body, so this thing is actually rotating in some sort of way. Or at least could be fixed, doesn't matter, but they just have to be attached to this guy. So basically what that means then is what? Each one of these guys, right, each one of the particles is going to have to be described then by 3 pieces of information, since I'm working in 3-dimensional space. So in this case, what this means then is each one of these has to be specified by a vector, which means we're going to have 3n worth of quantities that we're going to have to specify. Right? So 3 coordinates for each one times n number of particles, so we have 3n worth of objects. But again, since these guys are all connected to, say, something like a rigid body, something like that, which means I have m number of constraints, not all of these different vectors are independent from each other because they all have to be certain distances away, they have to be, etc. Which means that this is going to give an additional m number of coordinates, which means then that the total number of coordinates I'm going to need then is s is then equal to 3n minus m worth of coordinates, right? So I'm going to have to specify this thing in some sort of 3n minus m dimensional space. Okay? Now, one of the nice things about using the Lagrangian is even though we're losing some of its physical meaning because we don't really know what t minus u really is, right? All we know is that this thing is some quantity that we're calculating. But the nice thing is, since this thing is a scalar, what that means is that it's actually invariant under coordinate transformations, which means that no matter what coordinate system I work in, the Lagrangian has exactly the same meaning, which means we go about it in exactly the same way. So no matter what coordinate system that I'm working in, it's invariant under these coordinate transformations, which means the structure of the Lagrangian stays exactly the same from one coordinate system to another coordinate system. This is not true with something like Newton's second law of forces, because the complete structure of Newton's second law is going to completely change as I go from one coordinate system to another coordinate system. But the Lagrangian actually stays exactly the same. So what that means is we can use this to our advantage. So what this means is that instead of working in a 3n minus m Cartesian coordinate system, where everything has to be orthogonal to each other, and etc., what we can do then is use what are known as generalized coordinates, which are then some coordinate which fully specifies our system. These are things that don't have to be orthogonal to each other. They just have to be components of our system, which is going to fully specify our system. Now, we've already seen this when we were working with So for example, when we did the ball rolling down and we specified our system by the angle theta here, as well as the distance it traveled along here as y. Here, these were two things which were not completely, actually they weren't independent at all from each other. They're also not 90 degrees away from each other, but they're just something that actually fully specifies my system. So if I know exactly the angle at which this thing undergoes and how far this thing went in this direction, I can now fully specify my entire system. So what this means then is we can work with something which is called the generalized coordinates, where we're going to work with then 3n minus m different coordinates, or different objects, which specify the system. So these coordinates have to fully specify my system. So I can't use just any random 3n minus m number of different components, right? So if it doesn't fully specify my system. So I have to know exactly what's happening in my system given these particular components. Now, sometimes it'll be easier to deal with constraints in some sort of algebraic way or a differential way and actually fully specify and work with 3n worth of different components, and then directly apply the constraints using those Lagrange unidentified multipliers that we talked about when we did calculus of variations. So sometimes it's a lot easier to do that, but But if we do know exactly how these constraints are going to work, then we can actually input the constraints and actually, again, something like this, where we can actually specify our coordinates without actually having to use the constraint equations. But that takes a lot of time and a lot of practice for us to kind of get used to that. So these S number of coordinates, we can actually identify, instead of using, say, xi, we can instead go to some qj, or qi, let me write a qi in this case, where qi then is going to be equal to our generalized coordinate. So these generalized coordinates, again, are something which is going to specify all the ingredients that we need to be able to fully specify our system. And again, these things don't have to be orthogonal to each other. They don't have to even have the same units. So again, here I was specifying in terms of theta and y. This has units of radians. This has units of meters. They don't have to have the same units. They don't have to be orthogonal to each other. They can simply be the positions of the particles, or the lengths of rods, or the lengths of ropes, or etc. They don't have to be exactly the same thing. So here we then have to have a mapping between the actual physical coordinates, right, these Cartesian coordinates then, and these generalized coordinates. So our mapping between these things are going to be that what? Let's say we have x alpha I, right, where alpha in this case is going to represent the particle that I'm talking about. So this is going to go from 1 to 2 all the way out to n. And then I then is going to be the dimensionality, so this is only going to be 1, 2, or 3. Right? So this thing then is going to be equal to x alpha, which is then a function of qj, q dot j, and can explicitly be dependent on time as well. Okay? Where j here is then the number, which is 1, 2, all the way out to s, where again s is equal to 3m minus n. So these are the number of independent generalized coordinates that we need to fully specify our situation. Now, in general then, the derivative of this, i.e. the velocity, is going to depend on qj, q dot j, and the time as well. So here, since we're going to work with the generalized coordinates, we then have to inversely map then these guys to the position and then the actual velocities themselves. So again, this is a mapping which is going to go from Cartesian space to Cartesian space in terms of these generalized coordinates, but now we want to write the generalized coordinates in terms of Cartesian space. So the way we would do that is simply do an inverse map. Well, from here, since both of these depend on qj and also q dot j, then that means that qj and q dot j are going to depend on both x and x dot. Right? So good. So in this case, my inverse map, which then relates these two guys together, is simply just going to be the opposite. So here I'm going to get a qj that is equal to q. I keep writing g's. Good. So qj, which is a function then of what? X alpha I and t. And we also get that q dot j is then equal to q dot j, which depends on x alpha I, x dot alpha I, and the time. So these things here are what are known as the generalized velocities. And these things are again what are known as the generalized coordinates. Now, it turns out that for a particular system, the generalized coordinates that you can use, which means the generalized coordinates and the generalized velocities, are non-unique. We can choose pretty much anything that we want, which is going to fully specify the particular situation. So again, as long as they are suitable to fully specify everything that's happening within inside of our physical system, we can use them. So again, they don't have to be unique. They're not going to be unique. They're not going to give us exactly the same thing. Well, they shall give us the same thing. At the end of the day, the physics will be the same. But again, we don't have a unique set of generalized coordinates that we have to use in any particular problem. We can pretty much use whatever it is that we want to use. Again, as long as it fully specifies. So that means these generalized coordinates are non-unique. So in any physical situation that when I'm looking at, these things are non-unique. Okay. From here, we can then write also the constraint equations. So our constraint equations then, let's call those f of k, are going to depend on x alpha I as well as the time. And we want that to equal 0, so these are the algebraic constraints. And here k is going to run from 1 all the way out to m, which again corresponds to a number of constraint equations. That's what we have. Now, the space that we're working in, which actually is using these generalized coordinates, is no longer a physical space, because again, we're not thinking about it in terms of x, y, and z anymore. So this is not really Cartesian coordinates, but this is what's known as a configuration space. So basically, we're just describing our system in terms of this new type of coordinate system, where this new type of coordinate system is what's known as a configuration space. Now, just like a regular space, though, how the particle moves within inside of this configuration space fully maps out the history of the motion of this particular object. So how this thing moves within inside of its configuration space tells you exactly the history of how this thing actually moved, and different paths will tell you basically with different initial conditions. So again, as you use different generalized coordinates, the motion at which it moves within inside of this configuration space may be different, but they're all unique under the fact that they have been identified with these particular initial conditions. So different initial conditions will give different paths. So for example, I was plotting this thing in, let's say, Q1 and Q2, how this thing moves through. So this is telling you exactly where this thing is moving in terms of these generalized coordinates at any given time as this thing is moving through. And again, different paths would correspond to then different coordinate systems. Okay. Now, how do you choose your generalized coordinates? Well, that basically just comes with time. So the more and more that you actually use these things, it becomes easier to identify which ones are going to work the easiest. Typically, kind of one rule of thumb to kind of work on is, again, there's no unique way of choosing these, but what you want to do is try to choose them in such a way that your Lagrangian and your equations of motion are in the simplest form as possible. So they should be able to easily solve the system under these generalized coordinates. So again, if I use different coordinates, generalized coordinates, my Lagrangians become bigger and uglier and look kind of nasty, but at the end of the day, I'll be able to solve it. So I want to choose a system which actually makes everything as easily solvable as possible. So if I do that, then that's a good choice of generalized coordinates. But again, doesn't matter what generalized coordinates I use as long as I can fully specify my entire system. So in my generalized coordinates, what does then my Euler-Lagrange equation become? So how do I write down my Euler-Lagrange equation? So, first of all, we have to make a small modification to our Hamilton's principle, because now Hamilton's principle said that basically in real space, right? So in our Cartesian coordinate space, the path going from one point to another point in that particular space, then we want to extremize that particular integral, i.e. the action. But now, all we want to do is do exactly the same thing, but now we're going to work in configuration space instead of real space. That's the only modification that we have to work with. So again, so basically, how this is going to work is that it's going to use the fact that the Lagrangian, again, is a scalar quantity, and it actually turns out to be invariant under coordinate transformations, which basically means that, again, that if I have this Lagrangian expressed in x alpha I, and then this is going to be what? X dot alpha I then this is equal to the kinetic energy, which depends on x dot alpha I, minus then the potential energy, which depends on x alpha I. But now that we know the transformation between these guys, what we also know is, again, this is a scalar, this is also a scalar, so this is actually going to be the same thing then as t, which is then a function of qj, q dot j, and t, minus then u, which is now going to depend on simply qj and t. But this then is equal to simply the Lagrangian, which is a function then of qj, q dot j, and t. So basically, again, since the Lagrangian is invariance under coordinate transformations, means again it has completely the same structure, just now in different coordinates. So instead of this depending on x alpha I and x dot alpha I, it's now going to depend on qj and q dot j. Which means then that now we want to vary the integral, which is then the integral from the initial time to the final time. But now in this case, we're going to integrate over to q, or sorry, no, we're doing a time integral, so that stays the same. There we go. Of our Lagrangian, which now depends on qj and q dot j and time. Which means that again, by varying this thing and setting this equal to 0, the only thing that's going to happen then is we're now going to get to the Euler-Lagrange equations, which now this is going to be a partial with respect to qj minus then the time derivative of then the partial of the Lagrangian with respect to q dot j has to all be equal to 0. So this is now going to be the Euler-Lagrange equation in this new generalized coordinate system. Where again, j here is going to run over from 1 all the way to s, right, in our 3n minus m coordinate space here. So again, so basically, the Euler-Lagrange equation stays exactly the same. Okay, so again, this is our Euler-Lagrange equation that has exactly the same structure. So now we're just going to take the partial derivatives in respect to each one of these independent coordinates, these now generalized coordinates, instead of their Cartesian counterparts. So this thing, again, is what's known as the generalized momentum. So this is the generalized momentum in this generalized coordinate system. And then this thing is usually what's known as the generalized force. So this isn't exactly a force, because a force, again, I'd have to be taking the derivative of this with respect to an actual physical coordinates, not just some random component that I'm taking the derivative of. However, it's called the generalized force because it acts just like a force. So basically it has exactly the same type of meaning as the force actually does in this case. So, to make this thing valid, there has to be some restrictions on this. So for this to be valid, there are some requirements that must be met for this to be true. So let's talk about the requirements. So these are our required conditions. So the first one says that the forces acting on a system must be derivable from one or more potentials, except when there are constraints. So basically, so here we must have that the forces are derivable from one or more potentials. Again, except when constraints are involved. So these constraints can basically come from things like friction, things like that. So in those cases, we know that we don't have potentials when it comes to friction forces because they're non-conservative forces, right? So there's not going to be anything like that. So our constraint forces are going to be things that, or at least our constraints, are going to represent forces that aren't derivable from potentials. Condition number 2 is that the equations of constraint must be relations that connect to the coordinates of the particles and may be functions of time. So equations of constraint. So constraint equations must be relatable to the coordinates of the particles and may be functions of time. The second condition here is what's known as, so as long as our constraints satisfy this particular condition, these are what are known as holonomic. Let me use this one. So these are holonomic. Did I spell that right? Nomic, good. Constraints. Now, if these things do not explicitly depend on time, then these are what are known as fixed. And if they're moving constraints, meaning they do depend on time, then these are called something else. So if these are time independent, these are what are known as fixed, or what's called, we're going to try to pronounce this. And if these things are moving, meaning they do depend on time, that they are time dependent. In this case, they're called Romomic. I guess how you pronounce that. Anyways, now it turns out that these aren't necessary as far as the Lagrange equations of motion are concerned, as well as the Hamilton's principle. It turns out that we can actually generalize to any type of constraint that is outside of this, which are known as non-holonomic, and we'll talk about that later. So, basically, again, the point is that if we had n number of particles, instead of confining ourselves to coordinate systems which are specified by 3n number of conditions, or again, if I have constraints, m number of constraints, so in that case, I'm specifying myself to a s-dimensional space, which is then 3n minus m, we can work in then any type of coordinate system that we want to, where again, these things don't have to be 90 degrees from each other, they don't have to be even have the same units. We just have to pick some sort of objects that we're going to call our coordinates, i.e. our generalized coordinates, which fully specify our problem. The reason we can do that again is because the Lagrangian is completely independent of the coordinate system in which I'm using. It stays exactly the same structure, and as we've seen now, even the Euler-Lagrange equation stays exactly the same. So in that case, as long as we choose something which is suitable, which again specifies the entire system, we can then work with that and then fully describe our system and then use that to describe our system as opposed to these Cartesian coordinates or a real physical space. So in that case, we're just working in, again, what's known as configuration space instead of this real physical space. Now, in the next video, it's probably going to be a long one because we're going to go through a lot of different scenarios, do a lot of different examples to basically see how this thing works. Okay. So first we'll do a couple examples which deal with just basically talking about how to choose coordinate systems which are going to fully specify some sort of situation. And then from there we're going to look at some physical examples and then apply generalized coordinates to it and then solve it using the Euler-Lagrange equations. So, like I said, we'll do that basically in the next video.